Okay, tutorial 5, and this is chapter 5, Spectra and Properties of Organic Molecules from the SSPD. The SSPD is the Spartan Spectra and Properties database. That's a collection of about 300,000 or so molecules, and we've done geometry optimizations with a specific density functional model. It's this omega B97 XD functional that we show down here with a 631G star basis set. So we have geometries and energies and spectra at this level, and then we have some higher order functionals and bigger basis sets that we use for more accurate energies as well. Okay, anyway, we're just going to access this as a resource to get calculated spectra data for a set of molecules. We'll use molecules that we've already constructed, so either in 2D or 3D in previous tutorials. But we'll build these again quickly. Let's go and look at limonene. So we're going to look at the 13C spectrum of limonene. So first let's build that. Since we did it before in 3D, we'll build it in 2D this time. So let's go and select cyclohexane from the rings over here. Double click. Okay, then I'll describe. So click carbon, double click to make one of these a double bond. So we have a cyclohexene. And with carbon still selected, just drag out, and we'll make this the one position, one methyl cyclohexene. Let's rotate this around so you can see 1, 2, 3, 4. So sort of opposite the where the methyl is on the 4 side, we're going to add a function, an alkenyl. We'll add some carbons. But we can either do this axial or equatorially, and with the single bond selected, I'll just show you. It's not exactly clear. It's ambiguous, I guess, for the 2D drawing. So we could either end up with the R or the S chiral center here, and it looks like it's R in this case. If you remember from the previous tutorial with limonene, this is an S center. So you can fix that in a couple of ways. One way would just be you could go and grab a proton and say, hey, actually down below axially there's a hydrogen here, so this is equatorial, and therefore this is an S center. That's one way of doing it. Or you could just with the carbon selected, you could say, hey, this carbon is sort of equatorial, it's up above. And either way, once you've designated the stereocenter here, and you see limonene in the bottom of the screen in the lower right corner, this is the indication that it exists in the SSPD. Once you've done that, click on the view mode, and you can do that from the glasses icon either in the bottom of the 2D spectra pane, or you can do it at the top of the toolbar. So go to view mode, I'll minimize that, and let's retrieve this from the Spartan Spectra and Properties database. The way we do that is, you see the name down here, I've sort of referred to it a few times, just click on it and then choose replace. Click on the replace button. And this will take the structure that we previously had and replace it with the results from a density functional calculation. Okay, let's now go in and take a look at the spectra, the 13C spectra anyway, and we'll do that. You can access the spectra pane either from the display menu, and that's display menu spectra, or it sort of looks like an IR plot, or it's this icon in between the electrostatic potential map for surfaces and the spreadsheet, sort of up to the right. Okay, this will bring a blank pane down to the bottom of the interface, and then you just click on the add button, the green add button in the upper left. There's a few different tabs, so if you have something else selected, choose NMR, and then click on the 13C calculated. Okay, and the color in the plot is red for the shifts, the peaks, and there's a little bit of interaction. You can click on a specific peak if you want, and we'll highlight the shift associated with that, or rather the carbon associated with that shift in the model, or you can click on a carbon. And we'll highlight the associated peak. So either way. And so you can see there are these doubly bonded carbons here, these sort of sp2 alkenyl carbons, and the same over here. These are up at the high end, and down at the low end of the spectra, here's a methyl group. Okay, so this is the calculated spectrum, and let's now see how well this does compared to experiment. So we'll go to the add button again, and we'll choose just to the right of calculated 13C experimental. We'll click on that. You see it did a little lookup. It actually goes online and does a search of the NMR shift database, so the NMR shift DB out of the University of Cologne. it's got about maybe 45,000 or 50,000 13C spectra and maybe another 25,000 proton spectra. So it's a good resource for small organic molecules. Anyway, okay, so here's experimental data for limonene. And the way you can compare it, you can sort of see that experimental is blue. If you click on a shift, you can kind of see, okay, hey, here's 108 for this sp2 carbon here. And then the calculated shift, if I sort of click next to it, 110.1. Okay, so you can explore things that way. I guess if things are really close, for example, I think these are almost overlapping. It looks a little bit purple. You can use the zoom feature, the center mouse wheel on the Spectra pane to zoom in. So you can zoom in and you can explore that way. So here's one way you can compare things. I think it's a lot easier to just do that with the atom properties dialog individually for each carbon, and then you can use the molecule properties to look at the comparison, at least for the set of carbons, and I'll show you that in just a second. Okay, but I've zoomed in on a particular shift. Let me get back to the regular focus. So I'm just going to click on this cancel zoom, this little magnifying glass with an X on it. I'll sort of put the standard plot back on. And I'll go ahead and close this, and let me just mention what I was referring to before. If you pull up the properties dialog, you can do that either by clicking on the properties icon at the top. It's also under the display menu, or you can right click on the background and choose properties. But let's bring the properties over, and let's click on the properties of an atom. So let's look at the atom properties. So for this carbon, the chemical shift that was calculated is 133.6, and the experimental shift is 133.8. And I can hop around on different carbons and do 23.6, 23.5. I can hop around and look at different comparisons. So you can do it that way. If you actually just open the properties dialog and with no atoms selected, with the molecule properties dialog displayed, if you move over to NMR and click on this, you'll get a little bit of a statistical data. So comparing experiment versus the calculated, the mean absolute difference was 1.41 ppm. One sort of stinker, about 2.5 difference, and we could go and explore where that is. It was probably one of the alkynyl groups. And our RMS error is about 1.6, so less than 1.7 ppm. Okay, so pretty good. Okay, so this is limonene. Now let's go take a look at indigo. Okay, for indigo first, let's close what's on screen, and let's go back and take a look. Okay, so the proton spectrum of indigo. Okay, and we just built this recently in the 2D mode, so let's go back to 2D. It's pretty straightforward. So just pentane, another pentane, carbon there. Let's do double bond over here, and then we'll put a amine substitution here, and then put the phenyl groups here. Okay, so indigo. Okay, so we'll get into the 3D space, and we'll retrieve indigo from the SSPD. So indigo from the Omega B97 XD 631G star model, we'll do a replace. Okay, so now we have calculated data. Let's go in and take a look at the Spectra pane again. So the display menu Spectra, or this little Spectra icon, and we will add. Let's first add not the top proton, but underneath that there's a proton with no coupling. So basically where couplings are set to 0. So let's click on that first. Kind of a simplified display. Okay, so these will show the sort of unique protons, and there are 5 in this case. Okay, so you can either by clicking on the plot or clicking on the proton out here, you can select those. Okay, now let's go back and let's look at this in a little bit more detail. We'll go and let's take a look at the sort of a standard display with splitting. Okay, and let me sort of, I'm using the right mouse to drag over, and then I'm going to use the center mouse wheel to zoom in so we can see a little bit better. Okay, so you can now see here where they're doublets or where we have quartets. So So you can zoom in and analyze the splitting patterns as well. Okay, so I'm going to go ahead and close out of this, and we'll close the Spectra pane. And then next, let's take a look at, I think it's trans still beam that we take a look at. Okay, next we'll look at the IR, the infrared spectrum of trans still beam. So let's go ahead and close Indigo, and let's build trans still beam. Let's do that from the 2D builder. That's a little bit easier. We'll choose carbon, ethane, ethylene, and then just choose a phenyl ring. It's a little bit smaller. Okay, clean up. Okay, so trans still beam, we'll go into the 3D mode, and then we'll retrieve this from the SSPD as before. So we'll replace a nice planar aromatic structure. Okay, let's go look at the IR of this. Let's go to the Spectra pane. Let's add under IR, calculated IR. Okay, let's take a look at that. And this behaves sort of similarly. Let's go and here, let's look at some CH stretches, I guess. If you click on the plot, you'll be able to turn on a little probe, and you can move that probe around. So here's CH stretches up around 3,000. Let's go look at some of the aromatic vibrational modes down here around a little over 1,500. So the carbon stretching in the plane of the ring. So you see on both rings the vibrational modes. Okay, so so this is the IR display, and then you can also, I guess I should go ahead and display this. You can take you can turn on a display of tables on the left-hand side. In this case, so every calculated vibrational mode, no matter what the intensity is, you'll be able to individually go and click on from sort of the selection boxes over on the left-hand side. Let's go ahead and take a look at the experimental IR of trans still beam as well, just to give an indication of how well Spartan does, or the calculations do. So let's add the experimental, and this is actually a download from the NIST website. So no longer NMR Shift database, but this is the NIST Kim Webbook database. Okay, so qualitatively looks pretty similar. You can just like with the here, let's turn this off. Just like with NMR, you can zoom in as needed. So I'm going to focus in around here, around these sort of aromatic vibrational modes that we were looking at before, and let's just zoom in. So you see, you get pretty comparable overlap between the calculation and the experiment. Okay, and you can always click on the just to the left of the disc, the magnifying glass with the X to turn off any zoom, so to get back to the standard display. Okay, so trans to still beam and display of infrared spectra. Let's move on to the next tutorial, and I guess that will be, let's go, we can close this one. And we'll take a look at the tutorial number 6, which I think is graphics. Yeah, graphical models for organic molecules from the SSPD. So we'll get set up with that, and we'll take a look at this next.